Hi, in this video, I will go through the major topics that you need to focus on and revise before the final exam. In lecture one, we talked about how to use or how to find the resultant force or vector of two or more than two vectors. So what we did actually, we said we had two types of methods. The first one is the graphical method, which I will mention here in this slide. The second method, which is the calculation method or the mathematical method, we will talk about it in the lecture two. So in graphical method, what we said, if we have two vectors like these, V1 and V2, we can plot them. So we can always plot these vectors. So I can bring this vector here at the same length, the tail of this vector connected to the head of the first one. So like this. So now these two vectors connected to each other. Now to find the resultants, I just need to connect the tail of the first one, V1, with the head of the second one, the V2. So in the final form, it will look like this one. So S represents the resultant of these two vectors. So if you plot these two vectors on a graphical paper and measure the exact length of each one of them, and then when you connect the tail of this vector with the head of the other one, you can measure the length of this S vector. So the length represents, or the value of this length represents the value of the vector or the value of the force. In lecture two, we use the mathematical method to find out the resultant or the component of the resultant of a force. So for example, if we have now two forces here in this bracket, force F1 and force F2, if I want to find the component of F1 along the UX, it's the U-axis and V-axis, I can draw this force individually like this. So I take the V-axis in this direction and U-axis in this direction. And now I can find the component of this force, which is the 500 along these two axes. As you can see here, the angle between the V-axis and U-axis is not 90 degrees. So in such case, we can use what we call the parallelogram method. So in this method, I just need to complete a parallelogram by extending the components along V-axis and U-axis in this way. So if I complete the parallelogram here, I know all these angles from the main figure. So I can put these angles here, and then I can apply the sine rule and find out the component Fu. And also I can apply sine rule for Fv. The same thing, I can put these values, sine 45 over the Fv equals to the sine 30 divided by the force opposing the angle, which is 500. And then you can find the Fv. Also in lecture 2, we use another method to resolve or find the component of a vector. This is this method. We use this method when we have 90-degree angle between the components. So if we have two components like this, the axis of the components, the angle between the axes x and y is 90-degree, then we can apply Pythagoras rule. And in this rule, it's quite simple. You complete the triangle, 90-degree triangle like this one here, and then you can apply the rule, which is, for example, here, for this is the long side of the triangle, and you say f cosine theta, you get the component along the x-axis, and you say f sine theta, you get this component, which is the vertical component. So by this, you can find the component of the force, like this. And also, if you have two forces, you can use the same rule by finding the square of these, each component, and the square root, you find the force F, or the resultant F of two forces, Fx and Fy. In lecture 3, we use third method of finding the resultant force of two vectors, and this is what we call the Cartesian coordinates method. In the Cartesian coordinate method, we give the x-axis I, simple, and the vector along the y-axis, give it j, simple. And then we can represent the vector v by these two Cartesian coordinates. So for 2D or two-dimensional vector system, we can write the equation, for example, for the force or for the vector v1 by giving the components of the vector along x with the Cartesian coordinate along x. So the value of the vector multiplied by I plus the value of the vector multiplied by j. If we have another vector, v2, then we will do the same thing. And then the resultant of these two vectors, we can add the value of the Cartesian coordinates. So for example, the I coordinates, we add them together. So Vx1 here plus Vx2 along I plus the Vy1, Vy2 multiplied by the J coordinate. And then also we can apply the same rule if we have three-dimensional system. All we need to do is to add the Cartesian coordinate of the Z axis, which is, we call it here, give it K. So K is the Cartesian coordinate for the third axis. And then we can apply the equation same as we did with the second, or with the two-dimensional system. We can say V is equal to Vxi plus Vyi plus Vzk. So for example, if you have these two forces, 6 Newton force along the x-axis and 8 Newton force somewhere have an angle 30 from the x-axis. And you can see here we have x-axis in this direction, y-axis downward. So we need to follow the same convention here. So to solve this, we can find the component of each force, the 6 Newton and the 8 Newton. So for the 8 Newton, we can simply use the angle here, and use the Pythagoras rule. So we can say 8 cosine 30 and give it minus because the x-axis is opposite to the actual one, which is to the here to the right. In this case, we have to the left. So to the left, we give it minus. So we find the value of the Fx for the 8 Newton force, and also the component y for the 8 Newton by saying 8 cosine 60 or 8 sine 30, same thing. And then once we found the both components, both of them are negative because opposing the convention of the given in the example. We take these scalar values and each one of them multiply by the unit vector. So for the x-axis, we said unit vector is I, and for y-axis, the unit vector is j. So you say minus 6.9 multiplied by I minus 4 multiplied by unit vector j. And of course, the unit for the force for the vector is the Newton here. Now, same thing for the 6 Newton, we do the two components, and because the 6 Newton has no y component, we have only x component, then this is only x. So 6 Newton in Cartesian vector, we will have only I, so 6I, or 6 multiplied by unit vector I. So to find the total resultant or the resultant of these two forces, 6 and 8, we just need to add the scalar equations or the Cartesian equations for the force 8 Newton and the force 6 Newton. So we'll add the I of both sides together and add J for both sides. And because we don't have J for the second force, then this is what we get. 6.9I minus 4j plus 6I. And then the final Cartesian equation for the resultant vector is shown here. Now, also in the same lecture, lecture 3, we also we have been introduced to the unit vector formula, and we said that if we have it on a plot or on a graph paper, then we can find the the coordinates of the vector, the initial one and the final coordinates, and then from these two coordinates we can use this equation to find out the unit vector of the force. Also, we can represent this if we multiply the unit vector by f to find the vector formula of the force. Same thing for we did for the three-dimensional system. We need only to introduce the unit vector z k for the z-axis, and as you can see here, only we add the extra term representing the z-axis. Also, in lecture 3, we start getting some knowledge about the moment, how to find the moment, and we knew that the moment around any axis, if you want to find it using a force, then simply multiply this force with the distance between the force and the point of rotation. So this distance must be the perpendicular distance from or perpendicular distance of this force, which means that this force must have an angle 90 degree. In case you don't have 90 degree, then we said we can use another method, which we called cross product rule method. And this method represented here by this equation, moment will equal to r, small r multiplied by f. And r is the position vector, which is the distance between the point of rotation and anywhere from the force. Of course, F is the force vector. So we must represent the distance and the force by vector formula in order to find the moment. In lecture 4, we talked about the force coupling, and this is where when we have a force acting on a system, and we want to find the effect of this force on a certain point. For example, here, point O. So this force acts, we have to replace this force by a couple acting or moment around this point O, and also a force exerted on this point in the way similar to this one. So I can move this force here, and then I can find the moment of this force 10 when I multiply it by the distance from the axis going through that point O. So the distance here, 75 in millimeter, I change it to meter. So 10 times 0.075, I can find the moment around O, and also I move this force 10 kilonewton, and put it right on the point O. So the moment here, we can find it equal to 750 Newton meter. In case we have three dimensional system, then as we said before, we can use the cross product system or cross product method, and simply just put the unit vector ijk, and then put the quantities of each unit vector for the distance here. You put the quantity r for rx for the I, and ry for j, and rz for k. Same thing for the force. You put the values of each component, and then each axis, and then perform the cross product method similar to this equation to find out the moment around point O. In lecture 5, we learn how to plot or learn how to do the free body diagram. This is quite important in the coming topics, because the first thing you need to do when you solve any problem, you need to draw the free body diagram. And the way we said, the way to do it is first step is identify which body you want to isolate. For example, in this system here, I want to isolate this bar here. So I just need to highlight this bar. And then second, I need to draw the free body diagram for this part only by drawing only the external forces on this bar. Then third step is identify the forces at the contact. For example, force acting at this point B, and the force at the joint A. And then we show, of course, the direction. That's quite important. So show the direction of choice coordinates, axis, or sign. We call it sign convention. So then we can start analyzing the system. This is like what we do here. We isolated this bar only, and then I can take this to the side and put all the forces acting on this bar. When I complete the free body diagram similar to this one, I can start adding the forces, all the forces in the same direction, add them together. So summation of forces toward Fx, summation of forces toward Fy, and the moment around a certain point, all these must equal 0. So when I apply this rule, I can find the unknown force or the unknown moment for um, any section of the system. And in lecture 6, um, we did some practice on how to calculate the forces acting on truss, so truss system. And for example, in this system here, the first thing you need to do when you have a system, as we said before, need to draw the free body diagram. So for this system here, we draw the free body diagram by adding all the forces acting at the joints and as well as the external forces acting on the system, which is 2 kilonewton here. Sorry, here we have only one force acting on the system, external force, which is 2 kilonewton. The other forces are the forces reaction at the joints or yeah, the point of point A and C. And then we apply the rule summation of moment around any point must equal 0. And we find the unknown forces. For example, here we applied moment around C to find the unknown force AY, which is here. We found it AY is equal to 1 kilonewton. We keep doing this for all points and to find out the unknown forces at all joints. If we want to proceed and find the forces at all the points in the system or all joints here, we can do the same thing for each force, and we can take, for example, joint C individually as a point here of the truss, and put all the forces acting on this. So, for example, here for point C, we have a force for this beam and a force we found it before 2 kilonewton Cx, and force of this beam here we call it FCB, and force downward, which is the 1 kilonewton we found it before. We can find, when do the summation of Fx and Fy, we can find the unknown forces. And then we can, after we finish point C, we can go to other points along the structure, and we do it point by point. Just a reminder here, when you say here, for example, at point C, we find the force in this beam upward or going toward the beam or away from the joint. When I go to point D, I use the same force also because this is the same beam, DC, the same beam. So the force going inward, outward of the, or away from the joint C is the same force going away from joint D downward. And this will allow us to find other unknown forces. In lecture 7, we have been introduced to the efficiency and virtual work. And we had like this example, in the testing design of screw lift jack. Here in this figure, we were turning, let's say, this handle 12 turns and to lift this platform 24 millimeter, and the force applied here was 50 Newton. So we want to find out the efficiency of the system. So to find the efficiency, we know that efficiency is output divided by the input. So the output work represented by the movement of this platform, and the input virtual work is the rotation, the work required to rotate this handle. So we said that at that time we have two displacement here. We have virtual crank angle rotation, uh, and we have the delta H, which is the vertical movement of the platform. And we said that we can do the relation between change in the angle of the handle and the displacement in the lift here. And then we said from these two information, we can find the work output by multiplying the load on this uh, platform, multiplied by gravity, multiplied by the displacement, uh, which is here 24 millimeter. And then same thing, we can find the virtual input work, the work applied on the handle, by multiplying the force times the radial displacement, ds. Uh, and then once we found these two values, simply the ratio between them represents the efficiency. In lecture 9, we talked about center of mass and centroid, and we said that we have center of gravity when we consider gravity in the equation, and also we have center of mass when we consider only mass, and we have also centroid when we have geometrical shape. So we call it centroid, not center of mass. And we have another type of centroid when we consider the length. And in case we have area, then we said centroid here when we consider area only. Also, we use this table when we solve problems. So if you have any shape like rectangular area shape, then we can simply find the centroid by this rectangular area, which is the center of the rectangle. And also the triangular area, we use this these ratios to find X bar and Y bar and other shapes available in this table. And we also learn how to find the centroid of composite bodies. And we said that we can divide, for example, this body, we can divide it into four shapes, four areas, each area represented here by number 1, for example, which is square, here a rectangle, here a triangle, here a half circle. And we can refer to the previous table to find the center, the centroid of that shape. And then once we find the centroid of the shape, we can apply the moment around any point to find out then the centroid of the complete or the composite body. So similar to the this method here. In lecture 11, we learn how to do analysis of beam forces, so beam external and internal effects. And we had, for example, in this solved problem, we learn how to find the equivalent concentrated load and external reaction for a simply supported beam subjected to a distributed load, similar to this one. And same thing we said, to solve this kind of question, we need to find the centroid of each part. So we're going to divide this, for example, to one part as a big rectangle here. The other part is a triangle. And we find the centroid of each one of these, and then applying the moment, draw the free body diagram here by uh, giving all the forces that external forces and internal forces applied on this beam. And then we can start do the moment around any point using the centroid, of course, of each shape. And then we can find the equivalent concentrated load. Also, we learn how to do the shear force and bending moment diagram. And for example, for in this problem here, we have this simply supported beam with a force somewhere acting on the beam at a distance 4 meters from one side. We said that we can to find the shear force of each section. We can divide it into two sections here, the left side and right side, and we put all the forces and moments acting on each section. So now when I draw the free body diagram for both sections and apply the value of the reaction here, 1.6 kilonewton, and the value here of the reaction is 2.4 kilonewton. Now for this side, I can apply the force balance for the y-axis. So summation of all forces in the y direction, similar to this equation, summation of Fy is equal to 0. I can apply these two, 1.6 Newton minus kilonewton minus V. I find the value of the shear force V, 1.6 kilonewton. This force here is actually opposing the force other side here. They have the same values. So I can use the value of V and found by this equation and take it to the other side, the right side of the beam, and do the same thing, summation over Fy equal to 0. So I have V here already found, which is 1.6, and plus V 2.4. Or I can simply just apply this because this is the other side of the shear force, because we have one upward, one downward. So if I apply this, say 2.4 here, the action of this side, plus V, which is this side, then I can find V acting downward minus 2.4. Now, if I do the diagram here, you can see starting from 1.6 along the beam until I reach the 4 kilonewton, and it will be the same 1.6 at this point, but then suddenly it drops down because of the effect of this force 2.4, which is acting in a opposite direction, minus 2.4. So it's downward, and this 2.4 value remains constant until I reach to the end of the beam. I do the same thing for the moment. So I take the moment around the edge of each section. Summation of MO, moment around the section, or moment around the section of shear force. I can say summation of MR1 equals 0. So M here is unknown, but I can find the moment of the other of this force, which is 1.6 times the distance x, and then I represent the moment in terms of x. So 1.6 times x. I do the same thing for the other side, because this side actually, if this one x, the whole length is 10, so the remaining part is 10 minus x. So the length here 10 minus x. So I know that this is the force. I have reaction. I can say this force 2.4 4 times the distance 10 minus x plus the moment, the bending moment at this point, which is m equal to 0. And then I end up with this equation in terms of x. So m is equal to 24 times 10 minus x. Now, I can simply just substitute the value of x, any x value, you will get this shape, which represents the bending moment diagram. If you like, try it here. If you multiply this x value at x by the distance 6, so 1.6 times 6, you will get the value 9.6, which is the maximum bending moment occurred in this beam at this point. In lecture 12, we learned how to find the friction of any moving object or any object, any shape or any object moving on a surface. And we know that we need to find the value of the coefficient of friction, or we call it coefficient of static friction, because now we are dealing only with static friction. So the coefficient of static friction must be known between the object and the surface. And in this case, let's say, for example, in this problem, we had an inclined surface, and we found the balance of or the force P that required to move the crate or the box along the surface. And we said that to solve this problem, you need to first to draw the free body diagram, as we did before. And when you draw the free body diagram, we should put all the forces acting on the object. And in this case, we have the value here of P, which is unknown, but we know other values. We know the value of the weight of this this box, because we know the mass. We multiply the mass by the gravity, and also we know the coefficient of friction. And we can find from this, using this equation, we can find the friction force because of this coefficient of friction. So simply we said we multiply the coefficient of friction multiplied by the normal force N acting on the box. We can find N by using the angle here. So we know the angle, and we can simply perform the force balance in the x-axis, because P force is along the x-axis. So we can say summation of Fx equals 0. So we need to find all the forces in the x-axis. So here we have P cosine, the first one, P cosine 30, and also we have minus 0.25 times N minus the 490.5, which is the weight of the box multiplied by cosine 60. And when we reduce this, we can find the equation, the first one here. And the second equation is all forces acting in the y direction. We'll do the same thing for the y direction. And then we have two equations. We can solve them simply and find out the P and N. Just want to remind you here, the x direction, as you can see in this figure, and x and y axes are represented on the surface. So this is the y axis, and this is the x axis. So that's why we need to find the component along these two axes in these two equations. Yeah, by this, actually, we completed the topics that we went through in ENG 150. And I hope that you're gonna perform very well in the final exam. Good luck for everyone.